Hello guys, welcome in this new video. In this video we will be discussing about master's theorem, but before going to the master's theorem I want to point out some things that in this excel sheet there are some topics that is not mandatory to actually read them, but it's up to you. If you want you can. And one of those topics a couple of those topics are like the quick sort on singly linked list and the quick sort on doubly linked list. So I will just go in brief through them, but not in detail. Also, the when does the worst case of quicksort occur and why quicksort is preferred for arrays and merge sort is preferred for linked list is actually covered in the previous video as well. So these also are not required to go again and again through them. So before going to the master's theorem, just let's go and see what quicksort for singly linked list is and for doubly linked list. So basically in the quicksort on singly linked list we actually do not perform this quicksort to actually sort the singly linked list as discussed previously, and we actually used merge sort for sorting them because the fetching because these linked lists are actually a sequential are not actually in sequential manner, and they are actually stored in different parts of memory, and they are just referenced by only a single pointer that only allows us to go in a single direction and not back and forth. That is one of the reasons. And other reasons you can check out my previous video. And for the quicks, but the algorithm is still the same, and you can check out these where this algorithm actually in this we just do the partitioning of the subarray. First we check the like select the pivot, then partition the subarray, then we have two pointer approach, and after that we again apply quick sort recursively in the subarrays. Okay, so this is the code. You can check this out as well. And coming to the doubly linked list in this as well, the slight difference is that in this one we can go back and forth. So some implementation is same, but some difference is also there, so you can check it out as well. But still I want to point out that these the quick sort is not applied on linked lists to actually sort them. So moving forward, these topic where when does the worst case of quicksort occur and why quicksort is preferred for arrays and mass sort is for linked list is already discussed. Please do check out that video. And coming to the master's theorem, now I want to point out that there are actually two types of master's theorem, and master theorem is basically used to actually give the time complexity of recurrence relations. Okay, one is master's theorem for divide and conquer recurrences, and one is for subtract and concur recurrences. I do not know why they have actually told this theorem master theorem, but it is a master theorem part only, but we have to actually focus on the implementing part, means memorizing and learning part. So for this master theorem for divide and conquer recurrence, I would recommend you to not to go on this one, but to go to this advanced master theorem for divide and conquer recurrences. Here we have this function. This is similar to a this is a template similar to the recurrence relations that we will get. For those we can actually apply master theorem and find out the time complexity. So in here it's just tn equals to a t n by b plus theta n to the power k log power p n. You can also replace big O with this theta in place of this theta. So Here n is the size of the problem, and a is equal to number of subproblems in the recurrence, and a is greater than or equal to 1. N by b is size of each subproblem, b is greater than 1, k is greater than or equal to 0, and p is a real number. So whenever you have such kind of recurrence, then you have to check for some conditions. Let's say if the a is greater than b to the power k, so here a is greater than b to the power k, this one. So then you will have this t n equals to theta and log a base b, n to the power log a base b. Okay, and you have to just substitute the variable values here, like value of a and b here. Similarly, if a is equals to b to the power k, then you have to apply this one. And similarly, if it you have and then you have to check for p, and if a is less than b to the power k, then again you have to check for p's value, and accordingly you have to set the put the values in these. This is you have to actually memorize this only because it's a theorem, and this will actually help you in long run. So as previously discussed in the binary search video, we also discussed how we used master theorem to find out its time complexity. So here you can see that value of a is 1, b is this 2, k is 0 because n to the power k is n to the power k is actually 1 here, and p is also 0 because log to the power p is 0, that's why it's 1, right? And yeah, then we will just see which case is it. So as b to the power k you will do is equals to 1, so as a is equals to b to the power k, so this will be the second case. And also as p is greater than minus 1, so case 2a will be there. So the final time complexity will be n to the power log a base b and log power p plus 1 n, and just substitute those values in here, and you will get that time complexity is order of log n, right? Similarly, in merge sort we saw that the recurrence relation is this one, and accordingly we will find the values of a, b, k and p, and we will check for the case which case is occurring, and we will get the time complexity here. Okay, and in third example, fourth example, you can try these out as well. And coming to this for this theorem for subtract and concur recurrence, you have to just check for like these two things. See, there will be this relation, and you have to check for the values of a, b and n here only. The advanced version of this could have been also there, but for now you can just you see that it's some function that is again in in order of n to the power d. So you will apply this one, these cases you have to check. And if t is in t of n is in o order of n to the power d, if a is less than 1, and if a is equals to 1, then order of n to the power d plus 1, and if a is greater than 1, then the answer will be order of n to the power d a n by b. So you can check this proof as well. And yeah, this was it, and you can actually practice this as well. And yeah, that's the master theorem that is actually used for the recurrence relation solving and getting the time complexities. And remember that not all the questions can be done with master theorem, but mainly most of the recurrence relations can be, their answers and time complexities can be found by this master theorem. Okay, so till the next video, keep watching and keep studying.